Hello and welcome to this webinar hosted by Mango Solutions on Introduction to Python. My name is Christopher Hughes and I'm a data scientist here at Mango. I'll start with who Mango are, then move on to why Python. We'll then cover what's possible in Python with a demo and a coding workflow. And lastly, I'll leave you with some free resources for continuing to learn beyond today's demo. Some more about Mango. Mango are a data science consultancy based in the UK that has been around for almost 20 years. We regard ourselves as a trusted partner to enterprises that seek to become truly data-driven by embedding data science into their decision-making. We work within multiple areas in order to achieve this, with the three main focus areas being data science, data engineering, and data products. But why are we interested in using Python? When building a strong data science capability, data science teams are looking to cover off many areas of expertise. This is best covered by the Data Science Radar from Mango, which looks at the key areas to be communicator, data wrangler, programmer, technologist, modeler, and visualizer. By learning Python and integrating this with your workflow, you can begin to build a data science capability that covers all of these 6 key areas. There are multiple programming languages that you could use to do this, but why specifically choose Python? Python is an open source programming language that has been around for now almost 30 years. Python tends to be described as a language that is easy to read, broad in its application, and powerful in its performance. So it's really a great language for companies to adopt. On the right here are the Python principles, or the Zen of Python, that programmers try to stick to. Things like simple is better than complicated, and if the implementation is too hard to explain, it's a bad idea, and also readability counts. It is all about clear, readable code. This also helps with reproducibility, as when there are strong standards to program towards, we get better reproducible code. Python is also easy to install. A great position for beginners to start with is the Anaconda distribution. Anaconda provides you with interactive ways of using Python in succinct implementations and additional packages that are crucial for starting to work with Python in data science. Python also allows you to easily connect with multiple other languages, such as R, Scala, Java, and Spark, meaning you are not just limited to the world that Python creates when you are working within it. Being an open source language that is actively developed, there is a wealth of documentation written by the community to help you learn the language, understand the different functions, and find coding examples that someone else has used to solve their problems and that may be able to help you solve yours. These are standard documentation websites for Python, shown on the right-hand side, which are found for most of the major packages that you'll be working with. There is also an active Python community. The most popular community meetup in the data world is known as PyData, which happens very frequently all over the world. It's a great community to be a part of, and there is so much help available out there for you if you choose to learn it. So let's now look at what's possible with Python. We've talked about why you would be interested in it, but where can it help us? Python in the world of analytics has been very actively developed in recent years, and it has developed its ability to be useful in data science and advanced analytics. There are a number of libraries that have been developed to help those wanting to use Python in this way. Your data science toolkit, when you start in Python, will include NumPy and SciPy, Pandas, which is an incredibly popular library created by Wes McKinney, Matplotlib, a library for creating powerful visualizations using Python. But the world of analytics extends into the world of modeling, and Python is regarded to be the leading language in the world of machine learning, deep learning, and artificial intelligence. To cover off a few of the key libraries, we'll start with scikit-learn, which is the easiest package to approach machine learning with, as it contains ways of solving various problems, classification and regression problems for supervised learning, and for unsupervised learning, clustering algorithms are available, and all of these are written in a consistent, succinct framework, making it very easy for people to start working in machine learning. Another very famous library is TensorFlow. This is the Python package for deep learning and AI that has been developed by Google. It's mainly used for working with large-scale neural networks. It's very powerful, but it can be tricky to learn and understand. For that reason, Keras, a Python package, has been developed as a simple interface for working with TensorFlow or other machine learning packages. This is also now actively developed by Google, making it easier and more accessible to work with TensorFlow. There is also PyTorch, which is another deep learning library available out there. But let's now look at writing our own Python, working with our data science workflow, and implementing and using some of the packages and ideas that we've talked about up until now. What we'll look to do is start by getting some data, importing some data into our session, which we'll write in an interactive notebook. Once we have our data, we'll do some data inspection to see what our data set looks like. Then we'll move on to data wrangling. We'll start to do some base data manipulations, some summaries to see how our data looks and what we can do to change it. Then we'll move on to data visualization. We'll create a plot of some of our data. And then lastly, we'll do some base statistics and machine learning. So a small introduction into modeling using scikit-learn. So the first step of the process is to work with some data importing. We can work with many different types of data sources with Python, whether it be flat files, CSVs, which are very common, Excels. A lot of people will have lots of their data stored in various Excel workbooks, databases, or any of the native data types from other statistical software such as Stata and SAS. Now let's move to Anaconda Navigator. Open a Jupyter notebook, a notebook where we're going to write interactively our Python data workflow. If I switch to Anaconda Navigator, I can launch a Jupyter notebook. And that will open in my browser a Jupyter session where I can create a new Jupyter notebook. Create a new notebook on the right hand side using Python 3 underneath it. And now that I have a notebook, I can give it a name of Introduction to Python at the top and rename that. And here is where I can begin to write my code. The package that we're going to use to begin with will be Pandas, as that includes our data reading functionality. In order to use Pandas, I have to bring it into my Python session with my interactive notebook. I do that using the import function. Then I can pass the name of the package or library I want to bring in, pandas. I'm also going to give it an alias so I don't have to write pandas every time. I can refer to pandas as PD. Once that's imported, I can now use all of the functionality available as long as I use the alias PD first. Pandas contains lots of different ways to read in data, as we've spoken about before. We use the keyword read and then an underscore. We can see with a tab all of the different read functions that are built into pandas as standard. We've got read CSV, read Excel, read fixed width, from Google BigQuery, from JSON, lots of different ways of reading in data there available to us. What we're going to use for this exercise is read XL, and we're going to read in an Excel file. My Excel file here is a workbook with the tab Trans, which contains a data frame of transactions. So there are 72,000 transactions from different banks on different dates, accounting for different amounts and different operations. I'm going to read this data set into my Python session so I don't work with it directly in Excel, and then I can begin to inspect it using Python. In order to read that data set in, I want to use this function, all functions in Python followed by the parentheses, and then within that I pass any arguments that are relevant to that function. With read underscore XL, I need to give the path to the file that I want to read in. So I need to pass as a character string, so in quotes, the path to that transactions Excel data file. It's in a directory called data. It's called transactions. I can use tab for autocomplete. That gives the suggestions that are available to me. I also want to create an object in my session called transactions. So on the left hand side, I want to write transactions, which will be the name of my object. I want to use an equal sign. So now the data read in using readXL will create the object transactions containing all of that information from the data frame we've seen in the Excel file. To run that, I can use Shift or Command and return, and that will give me a star on the left hand side to show that code is running. When that's finished executing, I'll see the next number, so that's finished executing. Now I'll have the object transactions available in my session. I type transactions and use Shift Enter to execute that cell and move downward. I'll see all of the data that I'd previously seen in the Excel file. We've got the transaction ID, the account ID, type, operation, amount, balance, case symbol, bank, account, and date. So we have 10 different fields, 10 different columns within our data, as it says below, and over 72,000 different transactions recorded in there. What we have here when I've returned transactions, the name of the object, is the transactions information has been printed to my session, and it's used ellipses in order to not print to the console all 72,000 rows. If I just wanted to take a slice and see the top 5 rows, I could use a method of my object. Methods always follow objects and are separated by a period. And I can use the method head, which operates similarly to a function, so it has to have parentheses after it. So using the method head, that will return the top 5 rows of the transactions data. So there we are. We just have the top 5 rows of the transactions data that have been printed to the console. If I wanted to extract information about the bottom 5 rows, I could use tail. So where there is a head, there is a tail. That is a method that works in exactly the same way, so I need the period first, tail, parentheses, and if I use Shift Enter, that will execute that line of code and that will return the bottom 5 rows in my data set. And we can see from the row numbers on the side, the indices, that they are above 72,000, so these are the bottom values within my data set. If I wanted to return how many rows and columns there are in my data, I can take my transactions object, again using the period. I can then use an attribute instead of a method called shape. So we have methods, which are functions that are related to the object, specific to the object, that act on the object. And then we have attributes, which are properties of the object itself. So the tail method is a function that applies to the object, whereas in this case shape is an attribute, so no parentheses are needed. The properties of how many rows and how many columns are solely an attribute of the dataset. So using period shape, I can return that there are 72,000 rows, 72,042 rows, and 10 columns in my dataset. That's reading in data. Just as a recap, we're using the pandas package. We've aliased it to be PD, using import pandas as PD. We're using the read family of functions within that package to see all of the packages that are available to you there. You can look at read underscore and press tab, which will give us a list of all the read functions that are available. Here we've used readXL as we're trying to read in an XL file, an XLS or an XLSX file into our Python session. But we could have also read in a CSV, connected to a database, or use many different ways and many different data types in our session today. Next, after we've read in our data, we go back to our data pipeline. We've read in our data. The next step along is data wrangling. Data wrangling is all of the data manipulations that you may perform when you're doing your data science pipeline, your data analysis. This can be creating new columns in your data, removing columns in your data, changing the data type within a field, doing calculations based off the data contained in your data set, finding summaries, getting at statistical values such as the mean, the standard deviation. Any of these manipulations will fall into our category of data wrangling, sometimes data manipulation, sometimes data munging. And in order to do this, we'll again be using our object that we've created, our transactions data set, and more methods that are available to our data frame that we've created. So if we go back to our workflow, we can now do some data wrangling. We have our dataset transactions, but we may want to extract a column from there. To extract a specific column, we have to use square parentheses, and inside the square brackets, we have to include the name of the column that we wish to extract. So after the name of the object, transactions, which is our data frame that we want to act upon, we have to have square brackets. Inside there, we write the name of the column that we're interested in. All of the column names are character strings. They are words, so they all have to be encased in single or double quotes to tell Python we're working with a string or character. And what I will do now is extract the amount columns, the central column here, for the amount that is relevant for that transaction row. This will return from our data frame that we read in, transactions. This will return a series, which is just a column within our data frame. And we can see that's returned all of the transaction values for that column as a vector, a pandas series. We could then work with that series and do different operations, mathematical operations, as this is a numeric column. For example, we could find the mean of all of the values within that column. So again, we'd have to start by taking the transactions data frame, selecting the amount column. Then afterwards, again, we want to apply a method to this object. So we have to have a period followed by the method which we want to apply. If we're going to find the mean of this data, there is a method that is built in for mean. We're working with a method, not an attribute again, so we have to follow mean with parentheses. And that will return to the console, as we can see here, the mean of all the values in the amount column, and that comes out to be 5,509, and many decimal places. That's an example of one of the methods that we could use on a specific column, similar to when we were using methods on the entire data frame, as we did with tail and head. Next, we can look to do a greater summary using a different method called describe. So we're again going to select the same column, starting with the data frame first. In square brackets, we say which column we wish to be returned, that's amount, period, and then we have describe as our latest method, parentheses after the method, so that we correctly execute and apply the method. Describe is a wrapper method which gives back a series of base statistics that could be useful to us, including count, mean, as we saw before, STD is standard deviation, the max, the minimum, and then the interquartile ranges. So that's working with numeric fields, data manipulation, taking some summary statistics off that field. We could also take a column, extract some information from it, and then create a new column on our data set, so extending our data frame by an extra dimension. In our transactions data set, we have a date in the final column, which includes year, month, day. So using a specific accessor, we could extract the date from that field and then extract from that field the year, the month, or the day for whichever we wish to have. Following the same way that we extracted amount, we have to start with the name of the object, transactions, follow that with the name of the column we are interested in, which in this case is date. That will give us back this series, this vectorized version of the column from the data frame. From here, we then want to extract, let's say, the month. So in the first case, 1993, the 1st of the 5th, the 5th of January, or in the final case, 1998, December the 30th. In the first case, we would return the value 1 to represent the first month, if we were trying to extract the month, and in the final case, the value 12, as the final case is for the month of December. Slightly differently from when we were working with numerics, when we were applying mean or describe to the amount column, we have to use an accessor here to access the data type correctly, so we can then apply the methods in the correct way and the attributes in the correct way. So here, for a date time type object, we want to use the DT accessor, DT, And then after that, after we've used the correct accessor, we can then apply our methods and attributes as we would normally for numeric types. So if we follow that with the attribute month, that will return 1 for where we had the month of January 1993, January the 5th, and then 12 in our final case in our data frame, where we had 1998, December the 30th. So we can take a column, we can extract some information from it. The last step that we wanted to do was to create a new column within our data set using that information. So what we can now do is create a new column. It follows a very similar pattern to what we've used before, where we've used the square brackets in order to extract a column. This time we'll use square brackets to define a new column. So we'll take our transactions data set. We'll use square brackets, which would be to extract a column or define a column. In this case we're defining one. And then inside of our single quotes or double quotes, we want to include the name of the new column which we wish to add to our data set. So in this case, differently from month, as we have just done, I want to extract the year and have an extra column in my data set that represents year. I'm going to call that year lowercase, so it's consistent with all of the field names at the moment. Now I need to have on the right hand side of my equals sign what operation I want to assign to be equal to the year column within my transactions data set. Just as we've done before, I need to take my transactions data set and square brackets in date. I'm concerned with working with the date column. I'll need to use the date accessor in order to extract the attribute year, very similarly to how I've done above with extracting month. So here, I'm going to use the DT, the date time accessor again, and that will be followed by a period and year to extract the year. If I execute that with control return or shift return to give me a new line, that will successfully run, and that will have created a new column within my dataset called year. Have a look at transactions again, and I use the method head as we have done before, period head parentheses, and run that line of code. We'll now see that the data frame transactions has changed, it's been altered from what we had originally read into our session. In the first step where we were reading data in, we've now done some data wrangling, and we've manipulated our data set to add this new column to the end called year, which is a manipulation of the date column, extracting the year from each of the dates that are there. There are many, many different operations that we can apply in data wrangling. We can do calculations based on these columns. We can do string manipulations, so that's for using numerics, using strings, and we've just seen how to work with dates. So there are a whole host of ways that we can work with this. We can also query our data, cut our data, select specific columns of our data, sort our data, and there'll be a link at the end of this to show where you can see all of the different operations that are available to you. The next step in our data pipeline, we've first read in our data, we've then done some base data manipulations, so we've read in our data from Excel, we've extracted some information from our date using the DT accessor and the attribute year to create a new column year. We now may want to go and visualize our data. We have this data set with 72,000 rows, lots of information on, and we may want to quickly review our data or create a plot to report on our data set to a new audience. And for doing data visualization. There are functions and methods built into Pandas as standard, but we'll now introduce a new library which we haven't mentioned so far. So the next step is data visualization, and here are some examples of some data visualizations that we can use. Some faceted linear model plots at the top, some category plots or box and whisker plots with their outliers, and then some line plots as well. So we'll look at creating some of those now. The first thing we want to do in our new section of data visualization is read into our session a new package, a new library which we wish to work with. And this library is Cball. So we're going to import Cball. We're going to call this SMS as a shorthand for Cball. And once that's read in, we have available to us a whole host of different visualizations that we can quickly use to plot our data. You can see just as a few examples here, we have bar plot, box plots, category plots, and many other plots available to us within the Cball package, as well as other handling functions to help us create those plots. The first plot we're going to create is a linear model plot, just like we've seen on the presentation. The linear model plot function is called lmplot. To gain some additional information about the linear model plot function, we can use Shift Tab, and that will bring up the help documentation in a small box. If I press the addition, if I press the arrow next to the addition, we can then see all of the different attributes and arguments that are available to us for the linear model plot. So we have to pass as standard an x-axis for our data set, a y-axis for our plot, and then the data set which those two axes relate to. If I cross that off, I can now create my plot of my transactions. The two fields that I'm going to plot against each other are my two numeric fields. I'm going to plot amount and balance. Balance on my x-axis. Again, this will be within single or double quotes. It's the name of a column. And then on my y-axis, I have amount. That's my two numerics. If I run this, I'll receive an error. And I can see the type error is missing one required positional argument data, as there were three required arguments: x-axis, y-axis, and data. So I need to specify the data set that my balance and my amount come from. So I'll try that again. Balance, amount, and finally transactions. This time it successfully runs. It's going to be plotting 72,000 pairs of data, so it takes a little bit of time, but now it returns to my interactive session a plot of balance against amount, scattering all of those data points, and then a line for the linear model related to all of that data that I've just plotted. As that's quite a data-heavy plot, what I could do was apply a bit of data wrangling to select a specific bank from my data set that I wish to review, and then plot that data afterwards. So first let's go and do a little more data wrangling. Let's create a subset of my transactions data set for the bank IJ. I'm going to create a new object bank underscore ij, and that will be from the transactions dataset. Query the transactions dataset in order to form a subset, and my query will be where bank is equal to ij. And this will return wherever bank is equal to ij is true, and that will form the subset of my transactions dataset called the object bank underscore ij. To see what that looks like, we can again use the method head with the parentheses again, return that to the console, and we can now see we have a dataset which appears to only have ij in the bank field. Just to check the dimensions of that data, let's look at the shape attribute. And we can now see instead of having 72,000, more than 72,000 fields, rows within our dataset, we now have just over 4,500 in our dataset. So we've subsetted our dataset, which we can now plot. So we have fewer data points on our linear model plot. I'm going to do the Seaborn linear model plot again, using SNS as the alias to the package where the lm plot function is from. And then inside my parentheses, I want to include balance, amount, data, and instead of transactions this time, we're just going to use the bank ij dataset. That gives us a plot for just the bank ij dataset from the transactions larger dataset. If I wanted to break the data out across multiple plots, what I could do now is create a separate plot for each year. We have years 93 through to 98. We've created a column within our dataset for the year extracted from the date. I now may want to create a plot to see the relationship, the trend in our data through the years. In order to do this, I can use the same function again, linear model plot. I want to use balance against amount. For data, we're using the bank ij dataset, and instead of changing our original query to check and filter the data where bank is equal to ij and year is equal to a specific year, 93, 94, 95, and so on, and create a plot for each, I can create all of the plots simultaneously using the additional argument of column, and I can specify that I want to have columns of my data broken out across multiple graphs based on the year. This will form a new linear model plot for each year of my dataset. That creates 6 graphs, 6 linear model plots, one for 93, one for 94, all the way through to 98, each for the subset bank ij dataset. There are other plots that I could use. We've so far solely looked at linear model plots, looking at the whole dataset, a subset of the dataset, and then finally faceting that subset of the dataset across many years. I could also review the spread of data across each of my banks within one graphic. I could do that using a category plot. Using the function cat plot this time instead of lm plot. I want to see the spread of my amounts, but by bank. So bank will go on my x-axis, on my y-axis I want amount, because I want to see the spread of the amounts across each of the different banks. So bank IJ, bank NN, bank UV, ST, and so on. I'm doing this for my data set of transactions. We're using the full data set, not the subsetted version. And the kind of category plot I want to do is a box and whisker plot. If we scroll down slightly, we can see this has now created a grid with a box and whisker with all of their outliers created for each bank that was included in our data set, and that is because we specified the x-axis to be bank above. So we have bank IJ, the bank we've been using in our subset of data, in our first column, and then all of the other banks that are contained within our whole transaction data set. So just as a recap, we've started by reading in our transactions data set. This is our Excel workbook, reading in a specific tab from that workbook. We've reviewed our data to see which fields are contained within it, which values are there. We've checked what the dimensions of our data are, and then we've moved from reading in the data to data wrangling. Within data wrangling, we can work with specific columns, create summaries, do data manipulations, querying, arranging the data. What we focused on was creating an additional column in our data set. So adding to our transaction data set the attribute of year extracted from the date column within our data set. And then lastly, so far, we did some visualization. We took forward our data set, which had this additional column of year. We plotted it in multiple different ways. Firstly, taking a linear model plot to the full data set, going back and doing a bit of wrangling, extracting just the data where the bank was labeled IJ. We faceted, we broke out our data across multiple linear model plots by the year, and we also performed a box and whisker plot using the function catplot. So we've done two different types of graphs there, linear model plots, LM plots, and cat plots, and there are many others available within the package. The next part, after we've done our data manipulation, applied our data visualization to learn some more about the data, we could then move down our data science pipeline to modeling, statistics, and machine learning. The library that was mentioned before, where most of the statistics and machine learning functionality is for Python, is scikit-learn. So we'll now do a quick exercise of building our first model using scikit-learn on our dataset transactions, which has already been loaded in. So now we can take our transactions dataset and run it through a standard machine learning workflow, starting with defining our features and our target variable. In this case, as we'll be doing a supervised learning exercise, splitting our data into a training and a test set, then selecting our model and initializing it, fitting our training data to our model, reviewing our model by finally making predictions using our model, and then validating them against some performance metrics and criteria. So let's go back to our workflow and go on to our next section, which is statistics and machine learning. first thing we're going to do is bring in the relevant parts we're going to work with from the package scikit-learn. So instead of importing the whole part, we're going to import certain parts of the package. From scikit-learn, we're going to take from the model selection module, we're going to import training and test split as a function. We're going to use that to form our train and test set in a second. We're also going to import the model which we want to use. From scikit-learn linear models, we're going to import our linear regression, as we'll be using a linear regression model for our predictions here. So firstly, let's go back to our transactions dataset. Use the method head to review it. And the model that we're going to create as our first example is going to be a model that attempts to predict the balance at each transaction point. So what we're going to use here is balance as our target, and then we could use any combination of the remaining fields within our dataset as features for our model. But in this case, the only feature that I'm going to select, so it's the simplest model, is the amount. So we're going to see, can we predict the balance of a transaction at a transaction point based on the amount of the transaction that has taken place. So the first thing we want to do is split our data into features and targets. So our features for our transactions is solely going to be a data frame, including the column amount. I've used double square brackets there, as we're not looking to extract just a column, we're looking to extract a column, but to represent it as a data frame. And then y will be our target variable. In this case, that's the transactions. And we'll have that to be balance. So we're trying to predict balance using the amount of a given transaction. Our next step after we've defined our features is test and train split. So what we want to do is use the function we've brought in from scikit-learn above to split out our data into xtrain, xtest. So the train and test data sets for our features, and ytrain, ytest for our targets, both train and test. Now use the function that we've brought in, train test split. And what this will do is split our data out for our feature sets and our targets, given a test size. We set the test size to be equal to 0.2. That will mean 80% of the data is in our training, 20% of the data is held for our test. And I'll set a random state so that this can be easily reproduced. So we now have 4 objects, 2 objects for our training, 2 objects for our test. I now want to select my model. There's no feature engineering, no feature selection here, as we've already done the feature selection by picking the one feature of amount. I'm not going to do any manipulation to that. Now all I want to do is model selection. Here, we need to have our LM model, our linear regression model. I'll create that object using the class linear regression, which we've brought in from the scikit-learn package above. And now that I have that model, I can now fit my data, my training data, to that linear model. Xtrain, ytrain. I'm going to take my 2 sets of training data, my features and my targets, and fit them to my linear model. That's returned my linear regression, giving me the settings that have been included, meaning we've fitted our linear model. If I wanted to review what my linear model looks like, I can look at the coefficients, I can look at the intercept of the model, coef underscore to give me the coefficient, and intercept underscore to give me the intercept of my model with the axis. So we've now split our data into features and targets, divided our data into a training set and a test set, held the test set back, taken the training set and fitted that against our linear regression model. The last step is to make predictions and then validate our predictions against some performance metrics. For my balanced predictions, I want to take my model that I've just fitted, my linear model, use the predict method. It is now available as I have a model object, and pass it my features from my test set, so my X test will now give me a set of balanced predictions. We can now look at the balanced predictions by returning that to the console. And we have lots of different values in an array, which are predictions for our held back set of balances. The true balances will be within Y test. And we can see here we have a whole host of different balances from that set of data that was held back from the training and the fitting of the model. We can now compare our predicted values to our true values, our Y tests. So standard performance metrics for regression problems that we can use here are included within scikit-learn metrics. Within that module, we can import two metrics: the squared error and the score. We can now take our predicted values, our true values, and use these two metrics to return performance metrics for our model. Pass our Y test values along with our balance prediction to get a score. We can also return the mean squared error. Passing our predicted values and our true values, Y test our true values. So we now have two performance metrics to score our model against, to check the quality of our model. So now if we recreated a different model with a different feature set, we could have an easy comparison of which model was more suitable, which model performed better. So to recap, we've gone from the very beginning, reading in our data, going back up to the very top, reading in our transaction data using the read family functions from pandas. We've then done some data wrangling, some data manipulation to our data set before visualizing the data in order to see if there was any particular relationships between our data sets and the fields within it. And then lastly, we've taken our data set forward and walked through a modeling exercise of predictive power using our data set and a linear regression model. So that's where we're finishing with the code example. We've walked through our data science pipeline, reading, manipulating, visualizing, and modeling. But that's just a quick introduction to working with Python. There are many other things we can do. There's a lot I have not touched on there about the actual uses and the techniques within the modelling phase. I've just given an example of a modelling run-through. For more information about learning and resources, Learn Python is a perfect site, or Googling Learn Python for free to get you started. There are plenty of blogs, and as I mentioned earlier, meetups will be readily available to you, and I would strongly recommend those. Thank you for listening, and if you have any other questions about what we've gone through, contact Mango Solutions, and we should be able to help you with your journey of learning Python and building your data science team.